Industry uses a third of all the emissions in the world, and half of those come from just two materials, steel and cement. We use half a ton of cement every year for every person alive on the planet. My name is Julian Allwood. I'm Professor of Engineering and the Environment here at the University of Cambridge, and we have developed what we think will be the world's first process for making zero emissions cement. What we've shown already is that we can recycle cement by processing it through the same furnace where we recycle steel. And we know that if in future that furnace is powered by electricity that has no emissions, our process could make cement with no emissions whatsoever. Cement is a really difficult problem in mitigating the world's greenhouse gas emissions because we have no direct technical substitute for it. So what the industry has been working on for the last 20 years is making better use of the active ingredient called clinker by blending it with other materials so we can use less clinker and still get the same function out of the concrete. But although we can blend it, there are no substitutes for the active ingredient itself, and that's the fundamental problem to decarbonising concrete. Our process begins by demolishing an old concrete building. The old concrete gets crushed as it does today, but our interest is to crush it to a higher degree to separate out the old cement from the sand and the stones. Once we've got that, which we call recycled cement paste, then we can take it to the steel furnace where steel is being recycled. Because when you recycle steel, as well as the metal, you need a flux to bubble through the molten steel and purify it and then create a protective layer on the top so that the new steel doesn't get exposed to air. So we replace the conventional flux with recycled cement paste, and that turns out to work perfectly well for the steel makers, but it leads to a slag, the molten old flux sitting on top of the steel, that we can then harvest, and if we cool it in air quickly, miraculously it turns into new Portland cement.
So understanding the scale-up of this process is absolutely central. Here in Cambridge, we don't have the facilities to do that. In this country, there is one pilot-scale furnace that is something like 6 tons of steel, and it's at Middlesbrough. So our partner there, the Materials Processing Institute, is helping us upscale the process and understand how you go from a lab-scale furnace, tens of kilos, to this mid-scale furnace, which looks much more like the real deal. We should have, at the end of this month, our first industrial scale trials, where we'll be producing something like 60 tons of the stuff over the course of 2 hours. And we think we could provide about a third of the needs in cement in the UK within about 10 years. This cement is expected, because it's got the same chemical composition, to be as durable as the cement produced in any other plant in the UK. We think it's an important moment in the history of cement. I'm working with an amazing team. I'm really privileged and lucky to be doing this thing that is not only interesting scientifically, interesting industrially, but also important for the planet.
We're really excited about this innovation. I think potentially it's one of the biggest material breakthroughs that have come out of Cambridge in the last few decades. We have to wait to see, to confirm that it scales as well as we think it will before I can really make that statement with confidence. But before we started, there was literally no option on the table for making cement with no emissions. And this looks like it really could be a route to make a breakthrough in that most difficult of industrial emissions problems. So we're thrilled to be involved in it and really hope this is going to be big, obviously for the university, but for the country as well. We have the patent here, we're setting up the company, and there's every reason why this can be developed here and then propagated and scaled globally and at speed too.